We're going to start section 3.4, the derivative as a rate of change. A rate of change is movement. And what I said earlier was, why do we use S of t for a moving function? And the reason is a Latin word called meaning space. And some of them quote summa or sum. And again, we're measuring distance. So the S of t, the function of movement, is S of t. And it says displacement, and these are all vocabulary words that imply some form of derivative later on. Displacement, when the object travels a distance during a specific set of time. To calculate it, we put f of the change of the time and the change of it minus the origin of or start, and that's just distance. High minus low is displacement. And average velocity, we did this as an average earlier. And that says it's the displacement divided by travel time. So that means the destination minus the start divided by the difference or the amount of time that has transpired. And notice that we use the slope form of reference. All right. Because we're getting an average, that would mean a rate of change. And then we have the next one, which is velocity. Now we're getting into first derivative implies the movement at a specific point. And notice they still have the displacement function because this is also the what? Quotient. Difference quotient. So it's a derivative. And we're not going to be doing the difference quotient anymore. We're going to apply the rules of derivative. Is everybody comfortable with that? Velocity is the first derivative. And then we've got speed. And I had a problem earlier, and I think I left the negative on it. And speed is the first velocity, first derivative. Absolute value of velocity. That's how I'm going to write it, of the first derivative. It's the first derivative, but we take the absolute value. Well, you're going to ask me, well, what if the velocity was positive to begin with? We weren't going backwards. Well, then it is also the speed. Well, what if it's negative because we're going backwards? And then it would be the absolute value of that negative value. Now, you understand that zero speed is also possible in a moving function. Are we comfortable with that? At some specific point. Not the average, it's a specific velocity at a given x value. Is everybody comfortable with the distinction between the average and the velocity and speed? Then we have the nice one, acceleration. Acceleration is what sells a vehicle. It will tell you how much time it'll take to reach a desired speed. Acceleration. And that is the motor's function for power. Acceleration is what you determine. Okay, now I have a four cylinder, and my daughter has an 8. So when we go travel, when Jake, my son, puts the pedal to the metal, that 8 cylinder will kick in quick, quick. Mine will kind of get there, but not as quick. Again, force, ignition, power is all subject to what you build in a vehicle, and acceleration sells the car. For young people, I don't care. I'm just so there you go. 4 cylinders is good for me. All right. So acceleration is the double derivative of a movement of a moving function. And notice they put derivative of the first one of velocity over time is acceleration, and that's a small a. Now this next one is jerk. Jerk is the inertia causing acceleration. That ratio of depression on the gas against movement, that instantaneous chunk that the motor kicks in what force. So it is the third derivative. And notice it says it's the derivative of acceleration. The jerk, sometimes, depending on how old the vehicle is also an indicator of carbon buildup within the pistons and other mechanisms within the motor. That the jerk, it'll lock the car. So that's as much as I know about mechanics. My dad was a mechanic. So I worked with him on repairing some vehicles, and we had to clean the pistons for a lot of the cars that were raced. Really fond of the '56 Chevy. So we had to put in a Chevy, what was it? A Chrysler. We put in a Chrysler motor in that car, and that sucker could run. A little nuts. So now I can tell you firsthand some of the things that I did with my dad. I was free labor. I can't tell you how often I bled brakes. All right, so we're going to look at one of these positions. So here we're stating first off that we have an S of t because we know it is a function because it is structured as a what kind of, okay, so we've got some kind of movement here that is going downward and then line. So it says from the interval 0 to, so we're only measuring. So we want to find the body's displacement and average velocity for the given properties, correct? One of them is a derivative. Which one's the derivative? Velocity. The other one is math. It is the value of the function at 6 minus the value of the function at. Comfortable with that? All right. So in order to know the process, is that true? Are we seeing it? Okay. All right. Well, I need your help because I could make a mistake, as you well know. Okay, so we want to use our calculator because I don't want to make a mistake. So we want the S of 6 minus the S of 0. Okay, now let's look up here and make sure. There it is. The displacement is the difference of the outcome. Okay, is everybody comfortable with that? All right. Okay, let me look at my calculator here. All right, so on y equals, let me clear everything out we just did. All right, and we're going to enter our function as an x. It's a plus 6. Make sure I have it. So I'm going to do 6 and 0. And I get for 6, I'm at 0, and at x is 0, I am 6. How did that happen? What's the story here? This is in meters per second. Meters. We're talking distance, meters. Sorry. All right. The displacement is negative 6. And the reason is, did I put this function correct? Let me look. Yes. And I'm subtracting. The reason is that we started at the 6 meter mark. So the start was there. What happened at 6? Find out, right? So it must be touching the x-axis. Is it? Let me go zoom 6. It's going backwards down and coming back up, and it's at 0. So we can see now that the displacement value, because we started at 6 and we're ending at 0. So 0 minus 6 is as to movement. We've lost movement. And it shows the parabola is going up. Okay? See? No? Yes? No? All right. So we got the meter measurement. Now we want average velocity. Ooh, just divided by the change. This is not derivative because it said average velocity, which is displacement divided by, now they wrote it as the change, right? Displacement divided by travel time, which is the difference. So we're going to have that negative 6 divided by, okay, that is 6 minus 0, so that is a 6, and we have a negative 1. And this one is meters per second. And that is the average movement of this function from this point to this point. From between here and here, it's a negative 1. And that would give us a what kind of line? Say it. Because it's average. It doesn't take the curvature in concept, does it? No, it's a direct from one point to another point. What kind of line connects them? Yes, linear, because we know the slope is -1, right? Because we're connecting. But what else does? It's a secant, because we're taking 2 points. Direct line from here to here, and it's saying it's going from where it was to where it needs to be. All right. All good? Am I clear? I got a crazy look, right? All right. That I moved from 6 to 0. And so therefore it was negative 6 meters. It was the movement. Yes? Everybody clear on that? All right. Then it said it took time to get to that negative 6 distance. It took us 6 minus 0, right? Which is 6 seconds. So we divided by the 6 seconds and got a negative 1. Well, what is happening on this thing is a secant to here. And this is a sort of negative 1. And if we count how many movements of x, got our 6 going down. Sure? All right. Knowledge is one of those crazy things. All right, here we go. Okay, let's go to B. Is everybody breathing? B says find the speed and acceleration. Now, speed is the absolute value of what? Velocity. And velocity is a, yes. That was exhausting. So I'm going to do first speed. So if I have S of t described t squared minus 7t plus 6, then velocity of t, which is ds dt, velocity is going to be 2t minus 7. All right. And they want it, they want the speed at the endpoints. At the endpoint. So the endpoint is 6, right? All right. So we're going to first find the velocity. It looks like 5, and it happens to be the speed. And this is meters per second. So at that instantaneous point, S is 0, right here. What's my speed? 5 meters per second. So I did a tangent line, and we know it's going at that velocity. That velocity. Now it's already cruising. It's gotten its power, and it's cruising now. Right? Brain working? Yes. Yes.
If that function exists in that interval,
Because it said the endpoint on the information. Very good. The endpoint was 6. Question?
if I want to use 0, right there as well.
Yes. And at 0, you would get 0 because it's at the endpoint. You can't get that one much as you can get the other one. You have to get somewhere in between the distinctions or at the end. All right. That's a good question. All right. Now they want acceleration at the endpoint. And acceleration is double derivative. All right. Or we could say the derivative of velocity, right? So if I wanted a of t, I know that it is d dt of, sorry about that, velocity. And therefore, I would have, at this point, I have this guy right here, right? So, and this is in meters per second squared. Now, the square happens because in second derivative, and I might have failed you on that one, because it's d, let's say this is dt. So if I do the double derivative, it's d2 t s2, because the seconds become a critical component of measurement. All right. All right. So now I got that. Now what's the third one? C. Um, when, if ever, during the interval does a body change direction? And what we want is slope to equal zero. The derivative stops to change direction. And it is a sharp curve. Driving in the mountains of California, you know exactly what I mean. And go down. So these extreme changes is an instantaneous stop. Okay, so let me write some information that everybody can have. Okay, and the answer to that is when v of t equals zero. That's the first derivative, is velocity. V of t equals zero. So you can put it in your notes. At 3.5 minutes, it's when you have a vertex on this guy. If I did the math right, I think I did. That's the entirety of what you do, because there's no jerk on this one. But jerk is just after acceleration. Then you're getting into combustion kind of criteria. Now, if you're in the aerospace, you would definitely want to know. Maybe the astronauts feel the use of that much fuel at two, three, under 5 minutes. They use a ton of fuel to break gravity, the pull of gravity against that rocket, because it's gravity is not friendly. Once they get out, then they're fine. Okay, the people can lose consciousness and can lose body functions and things like that because the pressure is so heavy. I don't know. It was one of the Apollo, and the guy said that's what we have. It happens. All right. A lot of nerves too. Okay, so we have another one here. What is different between this one and the one we just did? What is the difference? It's ugly. I agree. So we have probably the quotient rule going on. I'm sorry, don't anybody get a seizure. It's not giving me more room for, oh, there it is. Okay. On this guy, we have our S of t in a rational value. Luckily, it's denominator as a single term, not a term with more than one. So it shouldn't be bad math that will get us. So here, our combined interval is 1, 2, 4 inclusive. Okay, not from 0, from 1. With S in meters and T in seconds. Find the body's displacement and average velocity. So our displacement is F of 4 minus F of 1. All right, very good. F of 4, actually it's S, but you get the gist. I can do the S of 1. Oh, it is. This is good. This one's 1. If I put in 4 here, I have 16. And minus 4. Oops, minus 4. Sorry about that. It's minus 4 because I forgot this part here. No, I did bad math. It's 0. And then the 1 makes it 16 minus 4. So we get going downward. And this was in years. All right, and now we want average velocity. So we're going to take our negative 12 and divide by 4 minus 1. So our secant line from point A to point B is a negative. All right, so that's our A. Our B is speed, acceleration. Okay, so we want speed, so we need the V of t, which is the first derivative. And that's going to give us, all right, so what's the derivative of a constant? 0. So the derivative of the top is 0. So does it matter that I multiply by t squared? It's 0. Does everybody agree? All right. So this is 0. And then, and so we have the 0 minus, and now we have the 16 times the 2t all over the t squared squared. Minus. Now we're going to do the 4. Well, derivative of the 4 is 0. So I'm going to put a 0 there. Is everybody okay? All right. And then I'm going to be minus, and now I'm going to have the 4 and times the 1 over t squared. Let's clean it up. Make sure I got this right. All right. So I'm going to reduce this guy. And that's a plus now. All right. So they want it at, let's see, at endpoint. This guy? Only because I'm bad at math. And it is negative, sorry. Oh, 2 errors in 1. Oh, my stars, bad math. Okay. So, sorry, that is going to be that. Okay, got it. Thank you so much. I appreciate that more than I can say. Okay, so now we got math. And this is 64, isn't it? Or over 16. And we're going to stick that in the calculator or expediency. And since I made a 32, I left 16 by itself. Forgot the 2. That's pretty unforgivable. I'm just going to put in the 4 over 16. Fourth is what I got. All right. Okay. And then it wants acceleration. Okay. So at acceleration, we know we want the derivative of the velocity. That was,
Isn't speed the
oh, this is absolute value. Oh, this is only that. I agree. I didn't answer the whole question. That's what happened on that last one. Velocity is a negative 1/4, but speed is absolute value of velocity. To put the notation, meters per second. Acceleration is the derivative of v of t, and this is what we had. So derivative is going to be a negative 32 times the t. I'm sorry, this is it. Oh, so it's 0. 0, I'll make it easy for me. 0, because I'm using that one, minus, and then I'm going to have 32 times 3t squared all over t to the 4th squared. Third. Why am I making that a 4? Job. And then I'm going to have minus, and I'm doing 0 again. And that will make it a plus 4 times the 2t all over t squared squared. All right. It is. Thank you. Absolutely. Okay. All right, so I'm going to take away the 2. Take away a t. I'm going to do a 4. That I'll have to tell you. I don't know what it is. Because that is going to be 4 to the 4th. for the 64. I'm going to stick that all in the calculator. I could reduce. Just want to get done. Oh, it's a quarter also. Right. And then it wants, when is it ever during the interval does it change directions? All right. Now, we have a rational guy. I don't believe there is any, well, I could be wrong though. Okay. Let's find out. I cannot speak without doing the math. So I'm going to move over the negative 32. Let's multiply. Divide by t. I'm going to divide by 4 first. And then I'm going to divide by t squared. Oh, at t equals 8 seconds, it changes direction. That must be where the asymptote would be. I don't know. I could graph it. Let's see what kind of, if I did good math, show up on my graph. Did it go negative on me? Is that what happened? Good that you graphed it. I love that. Just messed up on nothing. Okay, let's see what the graph looks like. Yeah, it's on the bottom. Oh, okay, 16. Let's look at that. Oh, it's below. That's right. It's going backwards. It's below. Well, that's interesting. 16t squared.
No, on the,
Oh, what is it? Oh, on my work. Let's look at that. I divided by t squared. What do you see? If I have 8t squared divided by t squared and I have t cubed, I end up with 8 equals t. Okay, and I'm going to stop right there. You've got a few more minutes. I will start right there. I think I have 1, 2, 3. 3 more problems. That's not an issue. It was cheesy math, and I'm sorry I made a mistake. So everybody okay? Everybody finish up the worksheet, and I'll pick them up.